Continuing on from our discussion of unitary matrices and Hermitian matrices, we're going to look at the matrix diagonalization of Hermitian matrices. So we'll start with a matrix A, which we have as an n by n Hermitian matrix. Remind ourselves that for Hermitian matrices, the adjoint of the matrix equals itself, and the adjoint of a matrix equals that its elements, you flip the rows and the columns, and you take the complex conjugate. We discussed unitary transformations as well. O is an operator in a given basis set. Omega is that same operator in a different basis set. To transform between the two basis sets, you find the unitary matrix, which is the overlap of the basis vectors in basis 1 and basis 2. So omega equals U dagger OU, and O equals the reverse transformation. Remember that the adjoint of a unitary matrix is its inverse, so doing the inverse transformation, O equals U omega U dagger. So as I mentioned, a unitary transformation is equivalent to a change of basis set from representing an operator in one basis to representing it in another. So let's now define a new matrix, little a, 2 lines under it indicating that it is a matrix here. A is the basis of A in which it is diagonal. So little a is related by some unitary transformation to big A because they are just 2 different basis set representations of the same matrix. Okay, so we know that A is Hermitian, and Hermitian matrices can be diagonalized according to some unitary transformation, but this U is a unique choice of basis set such that we are going to represent A in a diagonal form. So a diagonal matrix is a matrix which has 0 anywhere off of the diagonal where I equals j. So for an n by n matrix, you have n elements along the diagonal, and then everything else is 0, as represented by these bold zeros on the outside. So the elements of a diagonal matrix can be represented by some constant times the Kronecker delta, 1 if I equals j, and 0 otherwise. But it's also convenient that if we have a given Hermitian matrix, A, the diagonal representation of that matrix, its elements are actually the eigenvalues of A. So if we can diagonalize A, then we in fact have found all of the eigenvalues of A. The eigenvalues such that this matrix acting on a vector equals a constant times that same vector, the eigenvalues being all of those constants. Okay, so if we have a given eigenvector alpha here, so I have an eigenvector alpha, which is equal to the sum from j equals 1 to n of some coefficient times some given basis vector. So for each eigenvector I, there are n eigenvectors, each basis vector j, there is some coefficient which tells us how much of this eigenvector is represented by this particular basis vector. So there are n values of I, n values of j, n squared values of Cij. So j, as I said, are a set of orthonormal basis vectors. Omega are the orthonormal eigenvectors of this Hermitian matrix. So the question is, where do we get these coefficients from? There's n squared of them, so it seems like they would form a nice matrix. And the answer is, it's this unitary matrix which diagonalizes A. Cij is equal to Uij, which is also equal to, as I said, the jth component, the jth basis component of the ith eigenvector. So this unitary matrix which diagonalizes A under a unitary transformation, which gets A into the basis in which it is diagonal, is actually the matrix of the eigenvectors of A. So U is a matrix of the eigenvectors of A. So each column is an individual eigenvector, and each row is the representation of each eigenvector in a given basis vector. So to find the set of eigenvalues of a given matrix, all we need to do is find the diagonal of that matrix. We need to find how to diagonalize that matrix. So if we can diagonalize a matrix, then we can find all of its eigenvalues. And to diagonalize a matrix, we need to find the unitary matrix, which results in that unitary transformation to the basis set in which A is diagonal. So the entire process of finding the eigenvectors and eigenvalues of A comes down to finding the unitary matrix which will diagonalize A. Luckily, there are lots of nice computational algorithms which will do that for you. So for anything beyond a 2x2, that would be very difficult to do by hand. So what you can do is use some computer program, MATLAB, Mathematica, or your favorite programming language or linear algebra library, and find what this matrix is. And therefore, once you've found U, you have all of the eigenvectors. And then once you do a unitary transformation of A, you have the diagonalized A, which is all of the eigenvalues of A. So finding eigenvectors and eigenvalues of A is all process of finding the diagonal of A. So as I said, operators in quantum mechanics are going to be represented by Hermitian matrices, and the observable values of these things, things like energy, momentum, position, will be their eigenvalues. Things like molecular orbitals will be the eigenvectors of these kinds of matrices. So finding all the things we want in chemistry, finding the orbitals, finding the energies, finding all those kinds of things results to finding the correct matrix to express our operator and being able to diagonalize that matrix. So a lot of advanced quantum mechanics for molecules comes down to matrix multiplication, matrix diagonalization, and matrix transformation operations.